distributorless ignition, electronic fuel injection, sensor monitors, computer controls, and actuators. You need the most accurate, sophisticated, easy-to-use diagnostic power you can get to trace and identify elusive problems, solve them fast, and keep your customers satisfied. This video on diagnostic test pattern interpretation will help you understand the meaning of the diagnostic information you see on the test screens of the Snap-on Counselor 2 digital oscilloscope and relate it to specific ignition system performance problems. First, we'll talk about the value of testing strategies. Then, we'll cover the prerequisite testing procedures required to ensure valid test results. Finally, you'll learn how normal test patterns represent ignition system events and see how abnormalities in the patterns reveal specific performance problems. The Counselor 2 User's Manual contains detailed information about each of the diagnostic test screens and directions for conducting each of the tests. The manual also contains a wealth of background information that will help you interpret the test results.
You can start using the Counselor 2 without a lot of training because each test screen will give you much of the information you'll need. As you learn to recognize the patterns for normal system activity, you'll be able to spot abnormalities and identify problems simply by eyeballing the displayed information. With training and experience, you'll see more detailed information in the test patterns. There will be times when you'll want to freeze a waveform, expand it, or measure a portion of it to compare your test results to a specification. You may want to store the pattern in memory or print it so you can look at it again later. The Counselor 2 User's Manual and the video on basic operating procedures explain how to use these special features and functions. It's best to approach diagnostic testing in a systematic way. You need to verify that a problem exists, and you want to understand the scope of the problem. Are you looking for only one problem or several problems that might be masked by an obvious one? You want to eliminate areas of concern and reduce the number of tests you must make, but you don't want to backtrack either. Talk to your customer. Turn his or her complaint into specific diagnostic information that will help you do your job. When does the problem occur? Under what conditions? Do trouble codes point you in a certain direction? You may need to do a road test if you're looking for a hard-to-trace, intermittent drivability problem. Feel the condition of the belts and hoses. Look for physical symptoms that will help you locate the problem. Use your senses to gather information. Inspect the vehicle for visual defects. Listen for unusual noises. Do you smell gasoline or a burnt wire? You may need other equipment, like a scanner, a gas analyzer, or a timing light, to gather all the related information you'll need. Use your common sense to draw conclusions. Now it's time to bring the Counselor 2 into the investigation. Your preliminary findings will help you decide where to begin. Are you looking at a problem in the ignition system or in the cylinder's ability to build compression and produce mechanical power? Could the problem be caused by defective sensors or a faulty control signal? The scope gives you a variety of related tests so you can look at pieces of information from different angles. You can go from one test to another in any order you choose, and you can quit a test at any time. If you're not sure where to begin, start with a go, no-go test like the vacuum waveform screen in the cylinder test menu. This test monitors pressure fluctuations in the intake manifold. It will tell you whether the engine is okay mechanically, and it eliminates the need for time-consuming mechanical tests unless they are really necessary. If you don't have the optional probe that's needed to get a vacuum waveform, start with the cylinder shorting test screen. Next, use the secondary waveform for a quick check of the ignition system. Many ignition problems will show up here. Then, use the fuel injector waveform to check fuel system control. At this point, you may need to bring in auxiliary equipment or tools to analyze the fuel system completely or investigate mechanical problems. Before you use the Counselor 2 to test a vehicle, always refer to and follow the safety warnings, cautions, testing tips, and procedures that are necessary for the test you will be conducting. Always observe standard garage safety when you're using diagnostic equipment. These instructions can be found in the Counselor 2 User's Manual. Each time you turn on the scope, the first screen, the snap-on screen, will appear. Enter the correct engine information for the vehicle you're going to test. The Counselor 2 will test virtually any vehicle on the road with engines ranging from 1 to 16 cylinders. Be sure that the information you're getting on the scope is correct. Does the waveform look the way it should for the test you're conducting? Is information displayed as it should be? Do you see anything strange, extra or missing pulses, imperfect transitions, noise, etc.? Is the signal coming on at the right time? Is the duration of the signal correct? Is its duty cycle correct? Is the voltage amplitude correct? Does the waveform have the proper relationship to other waveforms on the screen? Be sure the lead set connections are correct and the signal you're getting from the engine is a good one. Don't use any test information that's erroneous, that might cause misdiagnosis and lead to faulty repairs or adjustments. Use the scope's self-diagnostic capabilities to check the continuity of the lead set, to test the scope's internal circuitry, and to verify that the keyboard is operating properly. Now let's look at the relationship between the 17 different Counselor 2 test screens and engine performance. When you learn to recognize the test patterns that represent normal system behavior, you'll quickly spot abnormalities that reveal specific problems. First, we'll look at the primary and secondary ignition waveforms and related test patterns that analyze ignition performance. Next, we'll look at the diagnostic waveforms that monitor the electrical integrity of system signals. Finally, we'll look at the cylinder test patterns that reveal the mechanical integrity of the engine. Remember, you can use any of the test screens in any order you choose. All spark ignition engines operate on the same principle. A mixture of air and fuel is compressed, ignited, and burned to develop pressure and force to produce mechanical power. Most engines use an inductive discharge ignition system to produce the high level of voltage needed to ignite the fuel mixture and begin combustion. Older ignition systems use breaker points to open and close the primary circuit. Electronic ignition systems use electronic means to control the flow of primary circuit current and ignition timing. Modern ignition systems are featuring more and more computerized control units as automakers strive to integrate engine systems. The main thing is that in both of these ignition systems, the principles of producing high voltage through electromagnetic induction are exactly the same. The basic waveforms for the primary and secondary circuits are similar. Distributorless ignition systems are virtually the same as electronic ignition systems, although they're arranged a little differently and operate on a waste spark theory. We'll talk about distributorless ignition waveforms in a moment when we talk about secondary ignition waveforms. First, let's take a look at the different activities in the ignition system. Then we'll talk about how the primary and secondary waveforms display the action taking place in the primary and secondary circuits. When the ignition switch is turned on, a low voltage current starts flowing from the battery into the primary winding in the ignition coil. As voltage passes through the primary winding in the coil, a magnetic field builds around both the primary and secondary windings in the coil. A primary triggering device turns the current off and the current flow suddenly stops. In a breaker point system, the points open. The abrupt change causes the magnetic field to collapse quickly and completely. This produces a self-induced voltage kick in the primary winding that multiplies the voltage in the secondary winding. The induced secondary coil voltage travels through the distributor cap to the rotor tip to the spark plugs. This voltage is high enough to ionize the air-fuel mixture and arc the gap, creating the spark that ignites the fuel and starts the combustion. The spark plug fires as soon as the gap is ionized, and the voltage drops while the spark burns. The remaining energy in the coil dissipates until the spark can no longer be maintained. The primary and secondary circuit waveforms basically look alike. Ignition events actually begin in the dwell section when the primary current comes on and ends when all energy dissipates from the coil. The waveform is divided into three sections: dwell, firing, and intermediate sections. The dwell period begins with the primary current turn on. Current flow in the primary winding induces a voltage in the secondary winding as a magnetic field builds up around both windings. The induced voltage shows up as oscillations in the secondary pattern. As the primary winding becomes energized, growth of the magnetic field slows and the oscillations diminish. Some systems have current limiting devices to control dwell. In these systems, you would see a current hump or voltage ripple. The primary current turn off ends the dwell period. Electronic ignition dwell may increase or decrease or remain constant with increasing engine speed. On a breaker point system, dwell is specified, but on electronic systems, it is not. The voltage spike, or firing line, displays the level of voltage that's required in the secondary circuit to overcome resistance and ionize the air-fuel mixture at the spark plug gap. When ionization occurs, voltage immediately drops because less voltage is needed to sustain the spark. This ends what's called the capacitive phase of the spark. The flatter spark line displays the inductive phase, which includes the visual flash and discharge of most of the coil energy. The coil energy decreases and resistance in the spark plug gap increases, as seen in the rise at the end of the spark line until the spark dies out. Spark duration is also known as burn time. When the spark dies, all remaining voltage is discharged as heat and the voltage decays. This is typically seen as 3 to 5 diminishing oscillations. Unused energy flows back and forth until no energy is flowing in either the primary or the secondary circuit. The cycle is ready to begin again with primary turn-on. Now, let's talk about some of the abnormalities you'll see in these waveforms, the problems that cause the abnormalities, and additional tests you can do with the Counselor 2. You'll want to compare all of the waveforms to see if the problem is affecting all of the cylinders or just one or two. Be sure to check the manufacturer's specification in a shop or diagnostic manual to verify what's normal for the system you are testing. If an abnormality shows up in the waveforms of all of the cylinders, the problem is going to be somewhere in the parts that are common to all of the cylinders, like the coil, coil wire, rotor, or primary triggering device. If the problem is in one or several, but not all of the cylinders, then the problem is going to be in the parts that are specific to the individual cylinder, like the spark plug wires, or connections, or distributor cap contacts. Call up the abnormal waveforms to examine them in more detail, and use the auxiliary tests to get more information. The primary menu gives you 3 tests for checking the primary circuit: the primary waveform, dwell bar graph, and duty cycle bar graph. The primary waveform is helpful when you're checking the dwell pattern of older vehicles with breaker point systems. primary current turn on and turn off should be consistent and proper for the system you are testing. The dwell period should be about the same length for all cylinders. Let's look at some of the typical abnormalities and see what they mean. A long dwell period means the breaker points are set too close or the switch turn on is too early. A short dwell period means the points are set too far apart or the switch turn on is too late. Intermittent point bounce, like this, is caused by point spring tension that's too strong. Point float is caused by spring tension that's too weak. When you want to check dwell values, use the dwell bar graph screen. The dwell bar graph displays dwell simultaneously as degrees of distributor rotation and as a % of duty cycle. So it's easy to compare actual readings to the specifications of domestic and foreign manufacturers. RPM is displayed so you can monitor the dwell response to changing engine speeds. On most electronic ignition systems, dwell can't be adjusted, and it may vary from cylinder to cylinder if it's controlled automatically. If the response is not proper for the system you're testing, the ignition control module is probably faulty. Excessive variation between cylinders could be caused by a defective trigger wheel, distributor shaft, or ignition control module on systems without automatic dwell control. On breaker point systems, dwell should be within a specification. Each cylinder should be about the same within 3 degrees. If dwell varies by more than 3 degrees, look for worn parts in the distributor shaft and bushings or a wobbly distributor plate. If dwell is uneven and evens out when speed increases, the problem is probably in the timing chain or belt. If only one cylinder shows a variation, look for a worn distributor shaft cam lobe. The duty cycle bar graph allows you to check dwell on electromechanical carbureted systems with feedback control. Use the second screen, the voltage screen, for the systems that must be monitored with a voltmeter. Check manufacturer's specs to determine what's normal for the system you are testing. Most systems will have a varying duty cycle but fixed frequency. Always check the frequency when you see an improper duty cycle reading. This will verify the number of signals per second being sent to the fuel control solenoid or the frequency control valve on some fuel-injected systems. If the frequency is incorrect, the control unit is probably defective. You can monitor signals with the Counselor 2 to check the operation of an electronic control unit and fuel control valve. For example, you can monitor the performance of the oxygen sensor by simulating varying operating conditions, such as when the engine's cold, when it's partially warm, when the air-fuel mixture is lean, when it's rich, and when the system switches from open to closed loop as the oxygen sensor heats up. If the duty cycle readings are incorrect during the test, check system wiring for continuity and connections for corrosion or tightness. If the values are still incorrect, the oxygen sensor or electronic control unit might be defective. You can also use the frequency display to monitor input and output signals for other sensors and actuators such as mass airflow sensors, manifold absolute pressure sensors, mixture control solenoids, engine speed, and spark timing signals. The frequency display shows how many times per second a signal's on-off cycle is repeated. You can verify that a signal is present and within specification. Use the lab scope screen in the diagnostic menu for more thorough analysis of sensor signals. The secondary menu gives you 4 tests for checking the secondary circuit: the secondary waveform, kV bar graph, kV histograph, and burn time bar graph. The secondary waveform is the most useful screen for checking activity in the ignition system since all of the secondary ignition components are represented. Plus, abnormal secondary patterns can alert you to other problems that affect combustion, such as too lean or rich fuel mixture, air leaks, or mechanical defects. Use the feature and function keys to expand the waveform, examine its details, and measure voltage levels. The firing lines and spark lines of all the cylinders should be about the same. Factors that affect the height of the firing line will affect the length of the spark line. If the firing line increases, the spark line will decrease, and vice versa. A spark line should level out at about 1 to 4 kilovolts. The heights of all the spark lines should be about the same. The spark line should be reasonably level and free of hash. Use the kV bar graph to measure the voltage requirement to fire each cylinder. Use the burn time bar graph to compare and analyze spark duration. A downward spark line slope is typical of excessive electrical resistance. This may be caused by high resistance in spark plug wires or connections. An upward slope is telling you that it's becoming increasingly difficult to maintain the spark. This can be caused by a fuel mixture problem or an air leak, which is creating turbulence. A steep upward slope suggests a serious mechanical problem. Spark lines with a steep, uneven slope downward indicate a large amount of resistance in the secondary circuit. This might be caused by a corroded distributor cap or plug connections. Excessive hash may be caused by burnt valves, a defective head gasket, a broken valve spring, distributor cap or rotor, spark plug or wire. A spark line that's longer and lower than normal can be caused by a rich fuel mixture. An excessively long spark line is characteristic of little or no internal resistance. Check the spark plug and gap conditions as well as the compression pressure. A shorter and higher spark line is typical of lean fuel mixture. No spark line at all is a misfire. Check the spark plug wire. You should see 3 to 5 oscillations in the intermediate sections. If you don't see at least 3 oscillations, there's probably a problem in the coil. If there are no intermediate section oscillations and no primary turn-on oscillations, the coil is probably shorted. Weak oscillations suggest leaky insulation in the secondary windings. The kV histograph screen is especially useful when you're tracing an intermittent drivability problem. This screen displays 256 consecutive spark plug firings, allowing you to pick up activities, like a misfire, that only happens once in a while. If you suspect a problem in a certain cylinder, you can watch that cylinder, or you can select the cylinder scan function to compare different cylinder data. If you press freeze while you're watching the live waveform, the Counselor 2 will hold the test patterns for all of the cylinders. You can examine them for more details later. The kV histograph lets you watch the firing patterns while you conduct the no-load, under-load, and snap acceleration tests. You want to see if the firing requirement stays normal during each test, or whether it rises or falls noticeably. If the voltage requirement wasn't normal, how many cylinders were affected? Is there an obvious pattern to the abnormalities? Keep in mind that changing engine speeds will affect the test results. Also, some patterns may look abnormal, but be normal for the engine you're testing. If the firing voltage increases during snap acceleration, but doesn't decrease immediately when the throttle closes, there's a lot of resistance in the secondary circuit. If the firing voltage doesn't increase when the throttle opens, but decreases immediately when the throttle closes, secondary current is leaking to ground. If the firing voltage increases dramatically when the throttle is open, the problem is in the internal combustion chamber. It may be a fuel problem. If the firing voltage is low during the no-load test and stays low during the snap acceleration test, the secondary resistance is very low. If the firing voltage is high during the no-load test and stays high during snap acceleration, the secondary resistance is high. As a general rule, if firing voltage is affected adversely during the snap acceleration test, the problem will be inside the cylinder. If the firing voltage doesn't change significantly, the problem will be outside the cylinder. Multiple problems that affect more than one cylinder can be hard to diagnose. Use the other test screens to confirm your findings. The kV bar graph screen makes it easy to measure and compare cylinder firing voltage requirements. Remember, this information is the same information you're getting from the firing line of the secondary waveform. Live firing voltages are displayed in graphic form, while the minimum and maximum kV requirements are presented as numeric values. RPM is also displayed, so you can note kV changes during a no-load kV test, a snap acceleration test, and an underload kV test. The normal firing voltage requirement varies from system to system. The Counselor 2 User's Manual will help you determine what's appropriate for the system you're testing. On an electronic ignition system, the difference between the highest and lowest firing line should be less than 50% of the highest level. After conducting the kV tests, look at the voltage requirement patterns. Is the kV requirement high or low for all cylinders? Is the kV requirement high or low for only one or a few cylinders? Is a low kV requirement seen on adjacent cylinders? Is the kV requirement high or low for every other cylinder? This will help you identify the factors affecting the kV requirement. As a general rule, if the minimum or maximum kV values change adversely during a snap acceleration test, the problem may be inside the cylinder. If the kV values do not change, the problem may be outside the cylinder. The burn time bar graph allows you to monitor the spark duration time, or burn time, for each cylinder. Spark burn time is the length of time, in milliseconds, that a spark arc is sustained between the electrodes of a spark plug. This is the same information that you see in the spark line section of the secondary waveform. Live burn times are displayed in graphic form, and minimum, maximum, and live burn times are given as numeric values. RPM is also displayed, so you can see how the burn times respond to changing operating conditions. The amount of voltage that's needed to maintain the spark will vary some, depending on conditions that affect conductivity, like the amount of current from the coil, or pressure, temperature, or turbulence at the gap. Normal burn time is about 1 to 2 milliseconds. The burn times for all of the cylinders should be about equal. A burn time of less than 0.8 of a millisecond is too short. More than 2.4 milliseconds is too long. Short burn times can be caused by excessive spark plug wire resistance, a wide rotor air gap, a wide spark plug gap, or an air-fuel mixture that's too lean. Long burn times can be caused by a fouled spark plug, narrow spark plug gap, or a shorted plug or wire. Emission controls that keep the air-fuel mixture lean may cause combustion to stop even though unburned air-fuel mixture is left. In these engines, burn times should be longer because the spark must be sustained for the duration of combustion. Now, let's take a look at the distributorless ignition system. The principles of distributorless ignition are essentially the same as those for electronic ignition. Distributorless ignition is physically different in two ways. There's no mechanical distributor, and most of the time, one ignition coil serves the two spark plugs of companion cylinders. You can determine which cylinders are companions by listing the first half of the firing order over the second half. Most distributorless ignition systems operate on the waste spark theory. Since the coil is connected to two spark plugs, the high voltage of the secondary winding is released simultaneously to both spark plugs. One cylinder is on the compression stroke while the other is on the exhaust stroke. The cylinder on compression ignites or is a true firing, while the other spark is wasted because it fires into the exhaust. The secondary circuit becomes capacitively charged as an excess of electrons builds on one side of the winding and a deficiency results on the other side. One spark plug fires forward from the center to the ground electrode with negative polarity, while the other spark plug fires backward from the ground to the center electrode with positive polarity. The Counselor 2 inverts the negative firing lines and displays them so they appear as positive firings on the screen. It's normal for half of the cylinders to be higher than the other half. True firing kV readings are typically in the 6 to 14 kilovolt range. Wasted firing kV readings are typically about 1 to 4 kV. The spark line is normal at 0 to 4 kilovolts. Increased resistance appears as a slight rise at the end of the spark line. After the spark extinguishes, remaining energy dissipates. This is seen in the waveform as diminishing oscillations. Use the secondary menu test screens to check distributorless ignition activity, firing voltage requirements, and spark burn time. You will get useful information from the no-load and underload tests, but it's not necessary to perform the snap acceleration test. Engines equipped with distributorless ignition and fuel injection systems respond too quickly to changing throttle positions to get useful information from a snap acceleration test. Since the Counselor 2 cannot be connected to the primary circuit on vehicles with distributorless ignition, use the secondary waveform to check dwell. The true wasted key will let you toggle between the waveforms of the cylinders with true firings and wasted firings. If you suspect a problem in the primary circuit, use the lab scope screen to check primary triggering signals. Now, let's see how these screens work together to help you diagnose an ignition problem. A customer complains about a rough idle and an occasional misfire when the engine's revved. The secondary menu test screens will confirm that this is an ignition problem. The secondary waveform shows an abnormally high firing line and short spark line on cylinder number 3. The kV bar graph shows a high secondary voltage requirement for cylinder number 3. The kV histograph also shows a high voltage requirement for cylinder number 3. The burn time bar graph shows a short spark duration for that cylinder. With a high kV requirement and short burn time, we conclude that there's a problem affecting the secondary ignition system for cylinder number 3 that's making it difficult for current to cross the gap. A snap acceleration kV test and an underload kV test can help you pinpoint the cause of the problem. In this case, it's a high resistance spark plug wire. You must be able to verify the integrity of a variety of sensor control signals if you're going to service and repair any late model engines. Automakers tell us that they intend to continue consolidating and reducing the number of engine systems, so we can expect to see even more integrated engine systems with computer controls in the years ahead. A single incorrect signal can affect the entire combustion process. You must understand the principles behind computer controls to trace problems to their source. Although there are many different kinds of computer control systems, they basically operate in the same way. Sensors are input devices that convert one type of energy, like temperature, pressure, or motion, into an electrical current. Thermal and pressure switches, timers, or variable resistors are some of the types of sensors used to monitor changing engine conditions. The input from a sensor goes to a computer control unit or module. The control unit has certain information that's specific to the operation of that engine burned into its memory. The computer compares the information coming from the sensors to the information that's stored in its memory. The computer then selects the appropriate command and sends an output signal to an actuator which converts the electrical current into a mechanical action, like opening or closing a switch. Some signals are generated voltage, while others are modifications of a reference voltage, which is supplied by a voltage regulator in the computer. Usually, signals are predictable repeating patterns that occur consistently in a certain time volts range. Most signals occur in the 0 to 5 volt range, much smaller than the 12 volt supply from the battery. Voltage signals can be categorized as analog or digital. Analog signals allow for infinite variability. This often results in a continuously changing signal that's displayed, such as a sine wave. Digital signals allow only two discrete variables, such as on-off or high-low. This often results in a square wave pattern. When the signal comes on, the voltage rises or drops to a specific level. When the signal goes off, the voltage returns to the original level. Sensors can send either analog or digital signals. The computer control unit converts analog signals to digital signals for processing. Output commands may be analog or digital signals. You must know something about the operating characteristics of the specific sensor, control module, or actuator you're testing to be able to judge whether the signal displayed on the Counselor 2 is normal or not. You may need to refer to a technical diagnostic manual for this type of information. Let's analyze how the two types of signals are generated and the abnormalities that reveal problems. Our first example is the variable reluctance magnetic sensor, which generates an analog signal by varying the reluctance of a magnetic field. The sensor has a magnetic pole piece or reluctor wheel and pickup coil mounted near a rotating metal wheel. The wheel accepts magnetism readily, but does not retain it. As it turns, notches or protrusions come into alignment with the reluctor wheel. The magnetic field varies in strength as the reluctor wheel passes the pickup coil, inducing voltage in the pickup coil. The rotating wheel generates a continuous alternating current as notches move into and out of alignment with the reluctor wheel, changing the polarity of the current. The waveform may have a sync pulse, which indicates to the computer that a new cycle of information is starting. Changing the engine speed will affect the voltage level. A good analog signal will result in a clean, consistent waveform occurring at the right voltage and frequency. If there's a sync pulse, it should occur with regularity. Additional or missing pulses may be caused by variation in pulse voltage levels due to stray metallic particles or a bad sensor. The Hall effect switch generates a square digital voltage signal as a small amount of voltage passes through a semiconductor material at a right angle to a magnetic field. The switch has a permanent magnet and transistorized pickup assembly mounted near a rotating wheel with shutter blades. The magnetic field induces voltage in the pickup assembly and turns the switch on. As a shutter blade enters the gap between the magnet and Hall element, a magnetic shunt is created, the voltage collapses, and the switch turns off. The abrupt on-off changes in the voltage level are displayed as a square waveform. The rate of the wheel's rotation doesn't affect the level of voltage where the switch turns on or off, so the voltage does not increase with increases in engine speed. Some digital signals display a signature pulse, which occurs when the number 1 cylinder fires. Some will have a computed timing notch. A good digital signal will have clean, square rising and falling edges where the current turns on or off. Any changes in the duty cycle or relationship of on time to off time, or the frequency of pulses, should be related to specific system events. A bad switch can cause irregular on-off switching times. A rounded corner indicates a grounding problem inside the switch. Hash that occurs when the switch is on can be caused by a defective switch. Most of the time, a circuit wiring schematic will help you locate appropriate test points. A breakout box connected in series with a computer wiring harness will make testing easier. A ground reference marker helps you to locate ground or zero voltage on the screen. A straight line, even with the ground reference marker, means no voltage is being monitored. A voltage trace above the marker has positive polarity. Below it, negative polarity. Alternating current will center at ground. If the whole waveform shifts away from ground, check the integrity of the ground wire. Some signals are synchronous to ignition events and should occur constantly while the engine is running. For example, the distributor signals the fuel injection system to start opening injectors when the number 1 cylinder is on its intake stroke. Other signals, like those from a manifold absolute pressure sensor, are asynchronous. These occur only when conditions change enough to provide new information. When you're testing a circuit with a switch-controlled mechanism, you need to know whether it's controlled on the ground side or the feed side to determine the proper test points. If the on-off control is located on the ground side of the consumer, it's ground side controlled. If it's located on the feed side of the consumer, it's feed side controlled. Remember, the consumer names the circuit. If you can't locate the control, check for voltage on the feed side of the consumer while the switch is off. If voltage is present, it's ground side controlled. If voltage is not present, it's feed side controlled. A device with ground side control will be receiving power continuously. When the switch is turned on, the ground path is complete and voltage falls to 0. When the switch is turned off, the ground path is broken and voltage rises to the original level. A bad connection will create hash on the bottom of the pattern. A device with feed side control does not receive any power until a switch is turned on. Its ground path is always complete. The on switch closes the feed path and the voltage rises. When the switch turns off, the feed path opens and the voltage falls back to 0. A bad connection will create hash on the top of the pattern. The first change in voltage, which begins the on period, is called the leading edge, whether the voltage goes up or down. The second change, which ends the on period, is known as the trailing edge. Once again, the direction of the voltage change doesn't matter. You will want to measure voltage levels, pulse width, or the amount of time a switch is on, and pulse period, which is the amount of time required for the total on-off cycle. To make these measurements, place the cursors at the appropriate points on the waveform. For the voltage level, this will be the highest and lowest points. For pulse width, this is the turn on and turn off points. For pulse period, it's from one turn on point to the next. As you can see, the distance between the two cursors is calculated automatically and displayed as delta V or delta T values. Once you obtain these measurements, you can calculate duty cycle by dividing the pulse width value by the pulse period value. You can also calculate frequency by dividing the pulse period in milliseconds into 1,000. This gives you the pulse rate per second in hertz. It's easy to check the duty cycle or frequency with the duty cycle bar graph screen. Once again, signals can have many different forms. You must be familiar with the characteristics of the signal you're testing to be able to know if the waveform you're getting is an accurate representation of the signal you want to test. You should know whether the signal is analog or digital, what the specified voltage amplitude and duration are, whether a device is controlled on the feed side or ground side, if the signal's duty cycle is fixed or variable, whether the frequency is fixed or variable, and what normal system operating conditions are. You should also be aware of outside factors as well as things you might do that can affect signal integrity. A straight line at 0 voltage indicates an open circuit or problems with the power supply, perhaps caused by corrosion. Monitor voltage at different test points in the circuit to determine the voltage drop. If the whole waveform is floating above or has settled below the 0 volts baseline, look for a poor external ground. Be sure to check the ground path between the actuator or sensors and the controller. General noise or extraneous voltage spikes can be caused by electromagnetic interference. Even test leads from the Counselor 2 can cause interference on test patterns if they're routed too close to an alternator or spark plug wire. Check the location of the sensor and its wires in relationship to spark plug wires and other parts of the engine. Computers are programmed to respond only to signals within a certain dynamic range and ignore others. Usually the spikes will be ignored if they are less than the highest and lowest peaks of the signal. Hash throughout the waveform is caused by loose wires or connections. Use a wiggle test to locate the problem. The diagnostic waveform menu gives you 2 test screens, the voltage and lab scope screens for testing sensors, control signals, and actuators. 2 other screens are dedicated to the alternator and fuel injector. The voltage waveform screen is designed to check and measure signals within a plus or minus 15 volt range. It's a good screen to use when you want to see that a signal is present and you don't need a lot of detail. The waveform may have a tendency to drift off the screen. To stabilize it, synchronize it with another signal from the engine or from the Counselor 2. Auto trigger synchronizes the waveform to the signal itself when the voltage rises at least 3 volts. If the Counselor 2 can't synchronize the signal, the waveform will sweep across the screen at the selected time per division speed. Engine sync will synchronize the test signal with another signal coming from the secondary lead, primary lead, fuel injector lead, or number 1 spark plug lead. If auto trigger doesn't work, try engine sync. A trigger marker shows you the point in the waveform where the signal is being synchronized. When you're monitoring a steady DC signal, the volts display is an average reading. When you're monitoring a varying signal, the volts display is still an average reading, but it's affected by the duty cycle. For example, if the voltage is on 50% of the time, the average reading will be 50% of the reference voltage level. If it's on 60% of the time, the average voltage will be 60% of the reference voltage. The number 1 plug lead must be connected to get an RPM reading. Use the voltage screen to measure voltage levels, pulse width, and pulse period. Then check your findings against specifications. You can check a voltage drop by measuring two test points on the same side of a circuit or on opposite sides of the connection. The lab scope screen gives you a tremendous amount of flexibility and adjustability for displaying many different kinds of low voltage signals in detail. You can measure minute variations such as excessive AC ripple on a DC signal. You can also observe and measure voltage levels throughout the entire circuit, even on both sides of a resistor, to locate problem areas. How the lab scope is set up will affect how the waveform appears on the screen. Just getting a valid waveform on the screen can be a challenge because individual signals vary so much from one another. When it first appears, it may look like a straight line until the volts time division is properly adjusted. What you are seeing is raw data with no explanation. This waveform has a time per division set too low. This one has a volts per division set too low. This one has a volts per division set too high. Here the time per division is too high and the volts per division is too low. Now let's adjust the time and volts properly. This waveform accurately represents the signal we want to test. The default setup will help you display a waveform on the screen by having specific parameters preset. If you don't know how to adjust a waveform, or if the waveform seems to be out of control, use the default parameters. To stabilize the waveform, use one of the trigger source options to synchronize it with another signal. If the signal is synchronous to specific engine events, like the firing of number 1 cylinder, trigger it from the number 1 spark plug wire lead, or the secondary or primary ignition leads. If the signal is synchronous to a specific signal, like the fuel injector signal, use the auxiliary lead to trigger it off that signal. If the test signal is asynchronous, that is, if it doesn't have a relationship to other engine signals, use the auxiliary lead to trigger off the signal itself. If you can't use any of these options, Run will synchronize the signal to an internal clock. Default setup uses the Run trigger source. Once you get a usable waveform, expand it, but leave at least one whole cycle and maybe part of a second cycle on the screen. The trigger point marker shows you where the waveform signal is being synchronized from. When you're triggering off the signal itself, set the trigger level voltage halfway between the waveform's highest and lowest voltage levels. The signal trigger point marker is the x-axis. The trigger level voltage marker becomes the y-axis, precisely locating the trigger point relative to time and voltage. The ground reference marker is relative. The AC option will magnify the alternating current component of the signal and let you see more of the varying characteristics of the waveform. If you're looking at the AC component of a direct current signal, the AC will appear to be centered at ground, but it's really at the top of the DC voltage. Signal invert enables you to display a signal upside down to view it or measure it more easily. This is helpful when you're testing a signal with negative polarity. One of the biggest advantages of the lab scope screen is that you can look at two signals to see whether they occur in correct relationship to each other. When there are two waveforms on the screen, the highlighted ground reference marker indicates which one can be moved. When two signals are displayed, the pulses of one may be associated with the pulses of the other in a specific way. The leading edge of one waveform may have a direct relationship to the leading edge of the other. Or, the trailing edge of the first may relate to the leading edge of the other. You also might find that a leading edge relates to a trailing edge, or both trailing edges relate to each other. You may want to use positive trigger slope when the leading edge of the pulse is significant, and negative slope when the trailing edge is significant. Let's look at a couple of related signals. First, we'll examine the relationship between the signal from the crankshaft position sensor, which is necessary for spark timing, and the signal from the camshaft position sensor, which is used to identify the beginning of the cylinder firing order and perhaps time fuel delivery. These signals go into the ignition control module with information from other sensors. The control module then sends appropriate commands to trigger ignition and fuel delivery. The crankshaft pulse provides crankshaft position information. The camshaft pulse is a reference signal that identifies the beginning of the cylinder firing sequence. The camshaft pulse usually occurs after top dead center when number 1 cylinder is on its power stroke. We are synchronizing the test signals with a trigger signal from the number 1 cylinder. The lab scope enables you to measure the phase relationship between these two signals to check ignition timing. But you must first calculate how many milliseconds are required for each degree of crankshaft rotation to make the lab scope measurement meaningful. Refer to a manufacturer's manual to find out how many degrees of rotation are represented by each square wave. You'll also need to know where the camshaft signal occurs in relation to the piston's position in the cylinder, which is usually specified as so many crankshaft degrees after top dead center. And you need to know whether the leading or trailing edge of the waveform relates to the other signal. Now you're ready to check the phase relationship. To convert degrees to milliseconds, use the cursors to measure the width of one square wave in milliseconds. Then divide that number by the number of degrees in the square wave. This gives you the number of milliseconds per degree. Convert the camshaft sensor signal specification into milliseconds by multiplying the number of degrees after top dead center by the number of milliseconds per degree. Position a cursor on the edge of the camshaft signal that's related to crankshaft position. Now, measure backward the calculated amount to find top dead center. Stop the cursor at top dead center and use the other cursor to measure backward to the edge of the crankshaft sensor signal. This is the ignition timing, where primary current is triggered and ignition events begin. To convert this measurement to degrees before top dead center, divide milliseconds by the number of milliseconds per degree. In this second test pattern, we want to check the two components of an engine computer signal that control ignition timing and provide input for fuel delivery calculations. Again, we'll synchronize the signals with the firing of cylinder number 1. This waveform is really two signals that are combined. The second leading edge to the trailing edge is part of PIP, the profile ignition pickup signal, which comes from the distributor and monitors crankshaft position and provides information for base timing. The leading edge at the front to the trailing edge is spout, the spark output reference signal, which triggers coil firing and regulates dwell. To verify that spark advance is occurring as it should, use the cursors to measure the width of one pulse period from the leading edge to leading edge in milliseconds. Then divide the time measurement by the number of degrees in one ignition interval. This gives you the number of milliseconds in each degree. Position a cursor on the leading edge of the PIP signal and measure backwards to the leading edge of the spout signal. Convert that measurement to degrees by dividing milliseconds by the number of milliseconds per degree. For this car, since the PIP signal, or base timing, occurs at 10 degrees before top dead center, You must add 10 degrees to the spout measurement to determine total timing. The fuel injector waveform screen monitors the control signal to an electronic fuel injector. The fuel injector is an actuator valve which opens to deliver atomized fuel into the intake airstream. There are two basic types of fuel injection systems that use electronic solenoid type injectors. The throttle body injection system delivers fuel through a central port in an intake manifold. A control unit synchronizes the fuel injector signal with a reference signal from the crankshaft, camshaft, or distributor. The multiple port fuel injection system delivers atomized fuel through ports positioned to spray the fuel at the stem side of the intake valve of each cylinder. Control signals may be sent to injectors in sequential spark plug firing order, to groups of injectors at various cylinders, or to all injectors at once. The pulse width of the control signal varies with changes in engine load, temperature, and exhaust gas oxygen content. Atmospheric pressure will affect the pulse width. Most fuel injector control units use ground side control in series between the injector and ground. The waveform is basically a square wave. The width is established by the turn-on and turn-off points. At turn-on, the ground path is complete and voltage drops to zero. When the current turns off, a voltage spike results from self-induced voltage in the injector's winding. Some injectors have current limiting. These waveforms display two spikes. The first occurs when the voltage is reduced, the second when it turns off. Keep in mind that waveforms for sequential multi-port injection systems will appear on the screen less often than when injection occurs at each cylinder firing. Fuel injector control located in series between battery and injector are feed side controlled. A waveform for a feed side control injector has the same features but is inverted. The width of the pattern changes with changing speed, but the pulse width may not. Pulse width changes with engine load, not speed. Problems show up as abnormal voltage spikes or erratic pulses. If the test is set up correctly, but no waveform appears, the reason could be that no control signal is present at the injector. This may be caused by a wiring or control unit problem. This test will not necessarily identify mechanical problems in the injector or other fuel system problems. The alternator waveform screen lets you monitor alternator output voltage and analyze the waveform to assess the condition of the diodes and stator windings, the two common sources of alternator problems. The alternator rotor has magnetic pole pieces mounted to a shaft which rotate within a group of three stationary windings. The fluctuating magnetic field induces an alternating current in each of the three windings. The three individual alternating currents combine to form a single overlapping three-phase alternating current. Diodes rectify the negative portion of the alternating current, converting it to slightly rippled direct current. Changing engine speed and load will affect the waveforms that are the basis of this waveform. Normal alternator current has regular, small, even ripples, all about the same height. If the alternator has been damaged seriously inside, the waveform may appear to be a straight line at a specific voltage level. If a waveform looks okay, but the voltage level is low, the voltage regulator may be malfunctioning. Diode or stator problems create very abnormal waveforms. An open diode results in uneven ripples. A shorted diode allows the negative portion of the alternating current to flow into the output wire. An open stator winding results in fewer ripples. A diode test requires a signal from the regulator terminal, such as the number 1 terminal on a GM Delcatron. If a diode trio is bad, there is a significant voltage drop. Instead of ripple, the pattern is expanded beyond the capacity of the alternator screen. Use the voltage or lab scope screen to examine details of the number 1 terminal. Now let's see how these screens help you diagnose an electronic problem. A customer complains that he's getting fewer miles per gallon and his late model Ford has less power since it was repaired. The mechanic who did the work insists there's nothing wrong. This will take some investigation to diagnose. Is it an ignition problem? The dwell bar graph looks normal. The primary waveform looks normal. The burn time bar graph looks normal. The kV bar graph looks normal. The secondary waveform looks normal. The kV histograph looks normal. The problem is not showing up in the ignition. The vacuum waveform looks normal, so it doesn't seem to be a mechanical problem. The cylinder time balance screen is normal too. It's not a triggering problem. The fuel injector waveform is normal. The pulse width is correct. This tells you that the fuel injector system is getting a good signal. But it doesn't tell you that the fuel injection system is operating properly. Use the lab scope screen to check the PIP base timing reference signal. The signal must be triggered off cylinder number 1. The problem appears. The PIP signature pulse, which triggers firing of the number 1 cylinder, is not aligned with the cylinder number 1 trigger point marker. The problem is distributor orientation or indexing. Check the position of the distributor. An engine may have many sophisticated controls today, but it's still basically an air pump that draws in air and fuel into the cylinders, compresses the mixture, ignites it to develop mechanical power, and then exhausts any remaining gases. When you have an engine problem, usually it's going to be caused by the ignition, the air-fuel mixture, or the cylinder's ability to build compression. Identifying mechanical problems can be difficult and time-consuming. Before we talk about the individual test screens, let's review how the cylinders alternately develop negative and positive pressure in the combustion chamber as the pistons move through each stroke of the 4-stroke engine cycle. This will help us understand what the tests are monitoring. Keep in mind that negative pressure is vacuum. On the intake stroke, the piston moves down, increasing space and sucking the air-fuel mixture into the combustion chamber through the open intake valve. Vacuum is created by the downward intake stroke. After the piston passes bottom, the intake valve closes. On the compression stroke, the piston is moving up to compress the air-fuel mixture in the combustion chamber. Pressure builds. Just before the piston reaches the top, the spark plug fires to ignite the air-fuel mixture. This increases the pressure even more until the energy of the burning mixture forces the piston down on the power stroke. Pressure falls as the piston moves downward. As the piston nears the bottom, the exhaust valve opens, releasing remaining gases and decreasing the pressure even more. The piston moves upward on the exhaust stroke, pushing remaining fumes out of the cylinder. Before the piston reaches the top, the intake valve opens. When the piston passes the top, the exhaust valve closes and the cycle repeats. The Counselor 2 lets you monitor cylinder performance at different points in the engine's operating cycle to verify that everything's okay, or to trace and isolate problems in specific cylinders or related parts. This eliminates the need to do labor-intensive tests on the induction system or camshaft valve train system that do not lead to problem solving. The cylinder test menu offers 2 screens, the cylinder shorting bar graph and a cylinder time balance bar graph, to monitor cylinder power contribution and ignition firing time intervals. 2 other test screens can be used if you have the optional probes. The vacuum waveform screen monitors the engine's ability to create intake manifold vacuum. The cranking amps bar graph checks the power required by each cylinder to crank the engine. Since the engine's ability to create vacuum depends on its mechanical integrity, let's talk about the vacuum waveform first. The vacuum waveform displays the fluctuations in intake manifold vacuum throughout the engine cycle. You can quickly see if there are any engine breathing problems. You can also pinpoint specific cylinders with mechanical problems. This test is not designed to locate vacuum leaks, nor will it identify problems that affect several or all of the cylinders, like a restriction in the air intake. To get a valid test pattern, you must connect the probe to a point on the intake manifold where it's possible to access vacuum from all cylinders. Usually, this is at or near the throttle body. Also, in this test, we're interested in analyzing the AC component of a DC signal. DC coupling displays the signal as a straight line at a specific value, similar to a needle-type vacuum gauge reading. AC coupling will display the AC ripple, which is like the jitter you see at the tip of the needle of a vacuum gauge. Note that the cylinder firing order is displayed on the top of the screen and identified as ignition. The cylinders that are affecting the vacuum level of the intake manifold are identified on the bottom. Now, let's relate cylinder events to vacuum fluctuations in the intake manifold. The intake valve opens while the piston is still moving up on its exhaust stroke, pushing some exhaust pressure back into the intake manifold. This incoming pressure is displayed as a rising waveform. The exhaust valve closes, ending the rise. Note that the peak corresponds to a specific cylinder. The pressure in both the cylinder and intake manifold drop during the intake stroke, while the cylinder is drawing the air-fuel mixture in. This drop continues until the intake valve closes. The point where the valve closes doesn't show up because the next cylinder has already begun its intake cycle. The next cylinder will begin its intake stroke before the previous cylinder's intake stroke is finished. The amount of overlap depends on the number of cylinders. A waveform for a 4-cylinder engine will be more detailed than one for an 8-cylinder engine because there is less overlap. The descending slope for each cylinder should be at the same angle and in the same time span. This tells you that the cylinders are developing the same amount of vacuum in the same amount of time. You may see some irregularities on the waveform that are caused by pressure waves echoing inside the intake manifold. These are normal. To locate problem cylinders, look for a sharp rising slope, a peak that's late or smaller than normal, and slopes that descend at an odd angle or different amount of time. Let's compare the abnormal test patterns from a 4-cylinder engine and a V8 engine. Look for a problem in cylinder number 1 of the 4-cylinder engine and cylinder number 7 of the V8 engine. Mechanical problems that affect the intake valve opening will show up in the waveform as a delayed peak if the timing is off, or a shorter descending slope depending on how much the opening is restricted. If a lot of vacuum is lost, the pattern for the adjacent cylinder may be affected. Here, excessive intake valve lash causes the delayed peak and short descending slope. This effect could also be caused by a bent pushrod. If a single exhaust valve is not opening normally, you will not be able to get a consistent waveform. The problem shows up as a sharp, almost vertical, rising slope. The peak is much higher than the others. A severe problem may affect several cylinder patterns. In this pattern, a worn exhaust cam lobe creates an excessively high peak. A steep rising slope can also be caused by excessive lash, a bent push rod, or broken exhaust rocker arm. Problems related to sealing the combustion chamber will affect the whole waveform. The leaking cylinder will have the shortest descending slope. The next cylinder peak will be higher than normal. A similar pattern will be seen when a piston is out of round, when there's a burned exhaust valve, or there's a piston ring problem. A cylinder with a major intake valve leak may have a violent effect on other cylinders. The highest peak belongs to the companion cylinder of the cylinder with the problem. Look for the cylinder with the second highest peak. This is where the problem is. To get the most out of the power stroke, combustion must occur exactly when the piston, connecting rod, and crankshaft are in position to give it. This requires precise ignition timing that varies appropriately with engine speed. When ignition is properly timed, fuel is burned more completely, providing maximum power and minimizing emissions. The cylinder time balance bar graph monitors the time intervals between successive cylinder firings and calculates the difference between the time for an individual cylinder and the average time of all cylinders. You can use this screen to test engines with or without a distributor. Most engines will have even firing intervals, although some V-types have uneven intervals. The ideal firing interval for even firing four-stroke engines can be calculated by dividing 720 degrees of crankshaft rotation by the number of cylinders. There will be a small amount of variance between cylinder times. If one cylinder varies significantly from the normal difference, a problem exists. There may be some problems with the valve train or compression chamber that will not create a noticeable variation in the pattern. You will have to do other tests to trace those problems. An engine running rough displays an erratic firing pattern. This is caused by improper primary circuit triggering. This is caused by a malfunctioning primary circuit triggering device on a distributorless ignition system. The cylinder shorting bar graph displays the force of each cylinder's power stroke by comparing the drop in RPM as each cylinder is kept from firing. There are two RPM readings. The top one is live. The bottom one freezes at the point when shorting occurs. The bar graph shows decreases in RPM as solid bars and increases in RPM as open bars. If you're testing an engine with computer controls, you should disable the sensors and actuators that will allow the system to compensate for decreasing RPM and mask the test results. The Counselor 2 User's Manual will tell you which sensors and actuators to disable on different models. Use the even-odd shorting screen to do a carburetor balance test on engines that have multi-bore carburetors or have dual injector throttle body injection and a dual plane intake manifold. This will show you if the primary bores are doing an equal job of supplying the air-fuel mixture. The RPM drop for even and odd cylinders should be about equal. With the cranking amps bar graph, you can check the power required to crank each cylinder through compression. The screen displays the amount of amperage the cylinder draws from the starting motor when the cylinder is in its compression stroke. This test is especially helpful when you want to measure cylinder contribution on engines where cylinder shorting cannot be done. The Counselor 2 prevents the engine from starting during the test by reducing the primary current level. Don't disable the ignition system. If you have a problem accessing the primary circuit, disable the fuel system. Charging system problems will show up after the engine starts and the cranking amps test is complete as a low amps value. This is a live reading from the alternator. Note the lowest and highest cylinder amperage values. Greater difference between the values indicates greater differences in cylinder compression. As a rule of thumb, if the difference is 10 amps or less, the engine is in good condition. If the difference is from 11 to 20 amps, there may be a problem that hasn't affected drivability or operating performance. Use the vacuum waveform screen or cylinder shorting bar graph to investigate potential causes. Differences that are greater than 20 amps are unacceptable. Look for compression or cylinder leakage problems. Repair any problems before doing any drivability testing. When a cylinder's compression is low, the cranking amp's value is low. The next cylinder may show a higher value because the starting motor suddenly draws a surge of current. An extremely high value indicates mechanical binding or interference. More testing is needed to determine the exact cause. Now let's see how the Counselor 2 screens can be used to diagnose a mechanical problem. A customer complains that the car is running rough. If you don't have the optional vacuum probe, go into the cylinder shorting bar graph. Cylinder number 1 is not contributing as much power as the other cylinders. The problem could be in the ignition, fuel, or mechanical parts. Check the secondary ignition waveform to rule out an ignition problem. Check the fuel injector waveform to check fuel system control. The signal is okay, but this does not eliminate a fuel delivery problem. Since the test results are inconclusive, auxiliary equipment is needed, or mechanical tests must be done to verify the problem. However, with the vacuum waveform screen, the problem is immediately obvious. The delayed peak of cylinder number 1 is characteristic of an intake problem. Check the condition of the intake valve, camshaft lobe, and cam follower.
This concludes our presentation on diagnostic test pattern interpretation for the Snap-on Counselor 2 digital oscilloscope. You'll find complete instructions for using each of the test screens presented in this video in the Counselor 2 User's Manual, along with other useful information that will help you interpret the test results. The Snap-on Counselor 2 provides diagnostic information that can be used to alter the performance of the vehicle you're testing. Be sure you understand the meaning of the information you're obtaining, and that the information is correct before using it to service a vehicle. If test data should appear to be incorrect, check the Counselor 2 User's Manual or contact your Snap-on representative. With training and experience, you'll develop the skills needed to trace and identify engine problems, solve them fast, and keep your customers satisfied.